So I'm going to review the only one exercise today, this hash map simple. Then I'm gonna try to be fast on this one so that I have time to do around one or five quizzes, something like that. I think I already looked into this one before. This is the implementation of a hash map. Forgot that I have to go on this one to go to the definition. So I think here what it's doing is implementing, as the name says here, the hash algorithm for both the i32 and string-slice keys. So basically, I assume that this is like the built-in implementation of the i32 in Rust. So it has all these different types of representing the integer. And what it's doing here, looping over the bytes of the integer and implementing this calculation, which is probably the hash. The way that the hash map works is that you have a key, then you run through the hash algorithm to get the value. And if you have conflicts, then I think you have multiple different strategies, but probably the most common one is to create a linked list from the value. So you basically create a pointer to another value on the same place in memory, from what I remember. And then the real implementation is probably going to be here. So this is the hash map. Have a generic key and generic value. And this is for the collision probably. So the node for the collision. The next is a pointer. The box is a unique pointer, I think, in Rust. And the node is like a self-reference thing on the type. The buckets is probably the root of the linked list, I think. Or maybe actually not. Maybe the buckets is just the places on the hash. I'm pretty sure that what this does here is constrain the type that k can be to things that implement this eq and this hashable, which is the type that has there on the beginning. It's basically saying the key has to implement both of these things. So it's a simple hash map that supports either i32 or string. And this eq I think is for equality and is one of the built-in types in Rust, I think. With a trait. I think usually you support this using a macro. So declare the macro on top of the struct, and then the macro is gonna automatically make the struct implement the trait. I think it's just something that allows you to determine whether or not the probably implementation of a struct is equal to another one. So like it's basically implementing equality as the name says. I think that's what it's doing. This is something that I've seen on the other ones as well. This layout, I think, it gets from this standard allocation, just basically manual memory management. It creates an array of memory with this type. Is an option to a unique pointer. The option is either some or none. Maybe that's the result. The result is either okay or error, and then option is either some or none. Some is when you have a value, none is when you have nothing. And this is a replacement for null, because in other languages, null can be problematic. So they did this one in Rust, which basically wraps the type, allows you to check whether or not you have something or nothing. Box unique pointer to the node. And uses the alloc to allocate memory based on the layout. As mutable pointer. These are the buckets. And you can initialize with this capacity. I'm not sure why he's using max 1 here. Maybe this is a mistake. So assume that this is like the vector implementation has. So in Rust, if you know you're gonna need at least a certain capacity inside of a vector, it makes more sense to initialize a vector with the with capacity function, because then you pre-allocate the memory instead of having the vector automatically grow its size when you hit the limit. It's just more efficient. I think it's basically the same thing, but then for our implementation of the hash map. And this is the reason why it uses the notation here, because then it forces the type you're gonna use to initialize the hash to have this implementation here. It forces the type to have this hash function, which is how the hash map is gonna keep the deterministic mapping between the key and the value. And this is basically the algorithm in both cases. It just changes how it loops. And probably the add implementation is going to be different depending on the type, maybe. And this is a problem I can't. So far, this has been the most annoying part of learning Rust. A lot of the built-in types are going to have these kinds of situations where you can't go to the definition because it's something weird going on with the. I think like they create an intermediate representation that the compiler turns Rust into, and then on this intermediate representation, you're gonna have this code here for these other types, I think. So it's kind of like obfuscated. It's annoying because obviously then you can't look into the definition. obviously based on the name, I assume that it's gonna add and then wrap around once it overflows, I think. But there's no way to know for sure if that's what's going on. Whatever. The index is going to be the hash of the key. Then it adds this to this buckets. This is the map, I think. So the buckets is a node. The node has the next. Yeah, so I think that this next here is for collisions. Yes, is the linked list for when you hit a collision. So the buckets is how many values you have for that index already. It finds the index by getting the hash of the key. Then it adds to the buckets. And then it loops over, I think. It loops over the buckets until it finds the key. Or until it hits the ends, I think. So I kind of get it. I want to obviously go deeper on the built-in things there. I'm just gonna ask GPT. But I think probably what I'm gonna have to do at some point is just look into the compiler implementation and then try to, or I'm gonna have to spend like, take probably a month or a week or something like that. And take just a lot of time to dive deep into the actual, all these built-in types of implementations. The rest I don't fully understand, like every single detail, but I understand enough of the nuances. It's very simple, actually, I think. I'm just gonna read GPT's response here.
It would add substantial iterator lifetime machinery without teaching much beyond what get underscore already demonstrates. Entry APIs and board lookup are omitted because they require broader trait design. Destructor panics can cause leaks during unwinding. This is not UB, but as with most zoning collections, destructors stored inside the map should not panic. Improved solution file rest use std alloc, self, layout use stdfmt use std marker phantom data use std. MEME trait for types that can be hashed. Implementations must satisfy two requirements. One, equal values must produce equal hashes. Two, a value's hash must remain stable while it is stored in the map. The hash function may technically panic, but the map avoids invoking it while performing structural mutations such as rehashing. Pub trait hashable for hash self, u64 fndj 2 bytes, u8, u64 11 5381 underscore u64 for byte time bytes hash hash. Wrapping underscore null 33 wrapping underscore add u64 from byte hashable hashable 432 from hash self, u64 djb2 self. To underscore l underscore bytes and hashable for str from hash self, u64 djb2 self, but as underscore bytes and hashable for string from hash self, u64 djb2 self. As underscore bytes node in one of the map separate chaining link list of pub struct node k, v pub key, k, pub value, v, pub next, option box node k, v. Caching the hash means growth never. Needs to invoke user defined hashable code after structural mutation has begun. Hash, u64, a hash map that uses separate chaining for collision resolution. The bucket array is manually allocated. Each initialized bucket contains an option box node k, v, while nodes inside a chain are normally by box. Pub struct hash map k, v buckets, mud option box node k, v, cap, usize, len, usize, impl k, v hash map k, v allocates and initializes cap buckets. Invariance established, cap 1, buckets is non-null and directly aligned. All cap bucket objects are initialized to none allocates underscore buckets cap, usize, mud option box node k, v. Assert, cap 0, hash map capacity must be non-zero, let layout array, option box node k, v cap. Expect, hash map bucket layout overflow, safety, layout is valid, non-zero layout for cap bucket values. Null is handled immediately below buckets unsafe alloc layout cast, option box node k, v buckets. Is underscore null alloc handle underscore alloc underscore error layout for index and zero cap safety, buckets points to an allocation for exactly cap elements. Index cap, each slot is written exactly once before any read occurs to unsafe buckets. Add index right none buckets. Meaningful changes cache node hashes each node now stores. Rust hash u64 this has three benefits. Growth invokes no user defined hashing code. Comparisons can reject different hashes before calling potentially expensive EQ. The structural phase of growth consists only of infallible pointer slash index operations and box movement. It does slightly increase node size, but it materially strengthens the maps invariance. Growth before insertion in the table now reserves capacity only after confirming that the key is new. Rust self. Reserve 1 the threshold uses the perspective length and exact integer arithmetic. Check capacity arithmetic rust old underscore cap. Check underscore null 2 prevents silent wraparound. Layout array continues to cache byte size and alignment related layout overflow. Narrow unsafe boundaries raw pointer manipulation is concentrated into bucket allocation, bucket delocation, index bucket access, access to the not yet installed bucket array during growth, iterator bucket access. All linked list traversal and ownership manipulation remains safe. Uniform linked list removal remove walks mutable links. Rust mud option box node k, v every node, including the bucket head, is removed using the same operation. This eliminates duplicated head slash non-head logic. Iterative clear and clear detaches each node's next pointer before dropping it. Under ordinary non-panicking destruction, this avoids recursively dropping an entire collision chain and potentially overflowing the call stack. No manual send or sync none were added. The raw pointer prevents automatic send slash sync derivation on current Rust implementations. Correct manual implementations could be written with appropriate bounds, but that would introduce another unsafe contract unrelated to the core allocation slash chaining lesson. For an early, simple hash map exercise, leaving cross-thread transfer unsupported is a reasonable intentional omission. Ratings category rating node safety 9/10 allocation and pointer invariance are localized and documented. Check growth and cache hashes remove major hazards. Panicking element destructors can still leak during unwinding. Correctness 9.5/10 correct replacement, collision handling, removal, growth, cache rehashing, and length maintenance. Deliberately lax shrinking and advanced board key behavior. Educational value 9.5/10 clearly demonstrates manual bucket allocation, initialization, separate chaining, link manipulation, cache hashes, and raw pointer back iteration. Idiomatic Rust 8.5/10 safe code handles nearly all ownership operations, default, debug, into iterator, and common methods are present. The custom raw allocation and custom hashing are intentionally non-standard for learning.
I'm just gonna trust here and copy there. It's not that big of a deal. And I think I already understand enough to... If it is wrong when I do the exercise, then I'm gonna review again. But I think I'm probably not gonna end up not doing this that much, I think, of reconstructing. But it's still good to go over the solutions and to just have as an option in case I want to do at some point. I think I'm gonna end up not doing the exercises. Probably gonna be... It's gonna make more sense, I think, to study real... or study libraries around the stuff that I'm doing and then implement things myself, obviously. But I think that probably the highest ROI is to study the built-in types and to study the Rust compiler. I think that's probably... It makes more sense. Or I should look into the best implementation, like do deep research first, to see the best implementation of each one of these structures from actual libraries, and then study that. I think that's probably better. But I think reviewing here, like finishing the review is probably good because it's gonna force me to think about implementation myself. I'm gonna go to the quizzes now. So one issue that I see here that could be a problem is the index, obviously, because it can be outside of the vector. But it's probably not what the thing is trying to test. So the assignment is the use of read memory. This assignment here. Hmm. So maybe because it accesses here, it could be the case. But this is only the reference. I'm not really sure. And this is like not creating, like the n is not mutable. But here, so it's assigning n to a mutable address, which is this index here, which is going to be 1, so it's a 2. This is mutable. Hmm. I think that the correct answer is probably A, but I'm not 100% sure why. The two things that I see that are weird is one is the index, which is obviously can go outside of the vector. This could be a problem. And the other thing is that this is not mutable. But the thing is that it is dereferencing the address here. So it's trying to change the vector through something that is not mutable. Because it is dereferencing, then I think it might make sense. Because it's not really changing the pointer. So like the n is a pointer to the place in memory, which is mutable. The place itself is mutable, and it would be the 2 here because that I is 1. There's the 2 element. Because the square brackets dereference the first pointer, and then you get the address to the value. So this is an address to a mutable value inside of this vector, which is true. And then when you dereference, you should be updating the value to this one here, which would be 1. The final vector should be 1, 1, 3, I think. If this works. But I think something to do with ownership, or else it's probably gonna fail. So it could be that when you do this here, you freeze the memories. Yeah, I don't, it is B. Yeah, I couldn't see like anything. I just thought that it was more likely that it would be A, but I couldn't find any explanation why it wouldn't work there. Also, if it was outside of the bounds, Rust would panic. Rather, you would panic at runtime rather than, yeah. So it's basically just saying that it would crash instead of using dangling pointers makes sense. Hmm. Okay. I think here it doesn't drop. So it's gonna be 3 first. Then here is gonna drop. There's something about the underscore, but I'm not really sure if, because it's using let, if it's gonna wait until the end of the closure to drop. I think that the first one is 3. And maybe it's 1, 2, and then 1 again. Because of the first one. I'm basically saying that so first spins 3, then drops this automatically, then drops this. Can either be this or it's gonna be 2, 1, 1. I think it's this one. Yeah. So it's basically saying that the underscore makes it drop immediately. And whether the program passes compiler, passes right the expected outputs of the program if it were executed. So either is obviously this one, and then right, it creates the enum with this string hello world, then it matches this. It's gonna be here, it's gonna get the length. I think it passes. It might be something weird. Actually, it doesn't because it is using the X on a match here, so I think it's gonna drop at the end. Probably an error. It's trying to use the X here and use it here. I think after he uses here, it's gonna drop the value when he goes outside of the closure here. So then when it tries to use here, it's gonna throw an error. But otherwise, it would get the length of the hello world and then print the value, I think. Yeah, so it was what I said. Pretty easy, that one. So this is the same one from before. Yeah. Yeah, what's up? It's a quiz Rust training. Yeah, kind of like a bunch of quizzes for Rust. Let me see. I think I put this on open GitHub repo. I I copied it initially from a known quiz site that I forgot. Yeah. 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 So basically go to this repo here. I think it's public. And then just run the commands here. Or you can look into the code and then extract whatever you want here. There's another site that I forgot. Yeah, this one actually, I think. So this is the site that I got the starting template from, and then I use an agent to improve and to add other quizzes from the Rust book. There's both this link here and this link here. No, I've been programming for 5 years, I think. I tried LeetCode, but I don't like very much because LeetCode is very like this. I just have like a resistance against education because education is just like brainwashing you to be a slave. So I hate education, like normal education, and LeetCode is kind of like the same vibe I get. I don't really care about the problems, and also the other issues that is not enough high density. Like the problems are just like they're not focused on the stuff that matters. These quizzes here are the best ones I found by far because they actually test like fundamental things about the language itself and then force you to understand like how the compiler sees the language. That to me that's like it makes a lot more sense. So I think that here is gonna actually this might be an error because it's using the same value twice maybe. Hmm. Yeah, assuming that no error happens here, then obviously the string is gonna be Alice or whatever is this. Then when it calls print, it's gonna print the name. There's Alice, so it's gonna print Alice twice. And because there isn't anything about drop here, I assume that's the only thing that. But I'm gonna say that's an error here because of it's gonna use the name on one, maybe on the other one, but yeah. So I wasn't very sure, but I think that's the reason why it fails. You try to use the same thing and then it drops after the first time you use. Yeah, it's moved into print and then try to use again. It fails. Yeah, so it's basically telling to use the reference here so that you don't move the value when you call the function. Pretty easy. So if I remember RC's reference count, it's basically as Rust, I'm not really sure. I think it doesn't have garbage collection, so you use this built-in type to get automatic garbage collection, I think. It counts the amount of references you have to the value. And I think I'm pretty sure this one is an error because I remember the quiz, but I don't remember why. But I think it has something to do with the RC implementation. It's cloning the n pointer to this value here, and then it's trying to change that. And I think it's because of interior mutability. So RC doesn't allow interior mutability. And if you want that, then you have to use refcell. I think if you want to mutate, basically what's happening here is trying to mutate the value here, the value of this. So the n is a pointer to the one value, and then n2 is going to be a pointer, it's going to be a clone of that pointer. It tries to change the value that n is pointing to by dereferencing this clone. And because RC doesn't have interior mutability, then it fails. I think that if you want to do that, then you could do like something like this. I don't remember how. Maybe it's new or something like that. And maybe it is like this. And then because refcell allows interior mutability, then it would work. But I think this is an error. Variance RC cannot be mutated because without use of interior mutability. RC enforces this property by implementing the deref trait, but not implementing the deref mut trait. I'm gonna search. Yeah, so according to the LLM here, it does. I think that the thing that I recommended there would work, probably. Yeah, so here, so it is exactly like I said it was when you wanna change. And just clones here. I think I'm gonna stop here. So this is probably an error because it's trying to use X twice here. There's a signs here which probably moves the value or moves ownership and tries to print. I'm gonna guess. Not sure why. Also, it copies instead of moving. If you use an reference there, I think that then you would fail. Also, the quiz is about teaching that if you do this with a string, then it's gonna move. But if you do with an integer, then it's gonna copy. And that's what it's about, because of the copy trait. So in Rust, just like in C++, I think there is this built-in types on the language that you can implement yourself or your own types. And then if you do implement, then it allows you to override the behavior. That's basically what it's saying. That the assignment here is based on the copy trait. So when you have a type that implements this, then it might change the behavior of what happens. Yeah, so I'm gonna stop here. Next time I'm either gonna continue to do this, but yeah, I'm probably gonna continue to do this stuff here. Trying to finish trying to improve this, and yeah, I'm doing like once I finish the TTS part, I think then I'm gonna do other stuff. But until then, I think I'm just gonna continue reviewing the solutions here and then doing some quizzes. So see you next time.